Muito boa noite a todos. Sejam todos muito bem-vindos a esse novo webinar organizado pela IGS Brasil. Hoje a gente tem uma enorme honra de ter aqui o Dr. First Koerner, diretor do Geosynthetics Institute. E como nos outros webinários, esse webinar ele tem um apoio da ABMS e um apoio muito especial da Geotecnia Brasil, um portal que a gente consegue transmitir essa comunicação nos vídeos do YouTube. A palestra vai ser em inglês e eu vou fazer uma introdução em inglês do Dr. First Koerner. E no final, se alguém tiver alguma dúvida, pode escrever em português nos comentários que a gente pode traduzir, tá bom? So, welcome everyone. We're very glad to have here Dr. First Koerner from the Geosynthetics Institute. This webinar is organized by the Brazilian chapter of the Geosynthetics International Society with the support of ABMS, it's the Brazilian Soil Mechanics Association, and Geotecnia Brasil, that's a YouTube channel specialized in geotechnical videos. So we were talking just a few minutes ago that the border between US and Brazil is closed, but it's very good to have tools like this one so we can communicate each other. So it's a great honor to have you here, Dr. First Koerner. We start in a few minutes, but first of all, I'd like to make your introduction. We are going to have a presentation today about quality control, quality assurance of waste containment systems. Dr. First Koerner is the director of Geosynthetics Institute. He's in charge of laboratory accreditation, field accreditation, and continuing education at the institute. He also manages several research projects, as has published over 350 technical papers in his 35-year association with polymers used in below-ground construction. Dr. Koerner's Ph.D. is from Drexel University in geotechnical engineering. He's a registered professional engineer and a certified quality auditor. Dr. George has received many awards of the year, the most notable being IFI's Environmental Technologies Award of Excellence in 1995, ASCE's GVGI Geotechnical Engineer of the Year of 2004, the title of ASTM Fellow in 2013, and GMA's First Koerner Lecture in 2017. So, again, we really appreciate your time. We know we're very busy, and thank you very much for accepting this invitation. So, this is your time now.
It's my honor to be with you. Thank you so much for this opportunity. If you want to reach out to me, do not hesitate through my email, which you see in red, or through the website. I respond quite readily, and I'm here to service you. So please, let's talk about quality control and quality assurance in geosynthetics and waste containment. This is an outline of the presentation, and you have to realize that this presentation is usually a 2-day course. I can't give that to you in an hour and 15, an hour and a half. I'll just give you the first 3 sections, particularly concentrating on geomembranes. This work, I have to acknowledge these gentlemen. Professor Daniel, Professor Richardson, and Professor Koerner all had a contract underneath Robert Landreth at the Risk Reduction Laboratory in Cincinnati. A lot of the information which I am presenting to you is from their work, and I certainly need to acknowledge and thank them as my mentors. As far as the background for this is concerned, you do have publications supporting what I am giving to you. The reference that I would suggest you obtain is the Daniel Koerner Waste Containment Facilities. It's an ASC publication. You, however, can also get this document, just about 90% of it, free of charge from the US EPA off of the internet. The objectives here, and we have to be very clear what the objectives of all this work that I'm describing to you is. It's certainly to minimize leakage, and the emphasis here is on the word of minimization. Realize that the target is to get no leakage, but in truth, the targets are to get leakage below 50 liters per hectare day, or that equals 5 gallons per acre per day. The QA personnel on site, whether they be field technicians, inspectors, or QA monitors, are there to improve the state of the practice of what's going on, and also to help out with communication. This is communication of the stakeholders on the project. And please realize that we are protecting the environment. We are truly stewards of the environment, and it's our task with this series of events to certainly minimize the risk to the environment. Liner systems that are out there, I realize they're different depending on where you are, but double composite liner systems are typical in the United States. Here you see that in cross section. We start from the ground up, the subgrade, and then typically a geomembrane, GCL, then a drainage net, a geotextile over top of that for a filter system. This is the detection system. Then another membrane GCL, which is a composite liner system over top of that. And here you see the entire liner system in its glory. You see the subgrade soil, the GCL, the geomembrane, the net, the textile, the GCL, the membrane, and then a heavy needle punch non-woven textile system. This liner system is replete with geosynthetics. We're typically doing long longitudinal cells, and it's staged and managed construction. Now let's go to the top side. You see again a composite liner system, typically of a GCL with a geomembrane over top of it. You have a gas venting layer underneath that. And then top side, you typically have a drainage geocomposite and then some sort of veneer reinforcement over top, and quite possibly a geosynthetic erosion control material over top of that. They're complex covers as well. This happens to be at a low-level nuclear facility at Savannah River. You see the cross-section. The geogrid was even installed for minimizing differential settlement in the cover. So you have the cross-section of the landfill. Here's the cover system. I even held back a little bit. There could be geogrids or geocomposites inside the waste mass if you wish. But at a minimum, the final cover typically has 7. Inside the waste could have 2, and then the base material has 9. That's 18 layers, folks, of geosynthetics. And if you're in the waste containment business, I argue that you're in the geosynthetic business. You have to be competent in this, and you have to know that these materials are tricky. They're not self-evident, and we'd like to show you some of these tricks in regard to this presentation today. In most cases, you are taking a geosynthetic and you're trying to make it equivalent to natural materials. Most, if not all, regulations allow this technical equivalency. The regulations, though, will rarely tell you how to illustrate that, and that's typically the role of an engineer. Nevertheless, geosynthetics have been generally accepted, and this table generated by Daniel Koerner and Richardson shows these equivalencies quite readily. When you have barrier systems, they typically in a natural material were compacted clay liners. For geosynthetics, they're usually geomembranes and GCLs or a composite of the two. The barrier system, geomembrane CCL, and then geomembrane CCL, GCL is quite typical. As far as drainage layers are concerned, they're typically sands and gravels in the natural environment. These have been replaced in large part by textiles, nets, and geocomposites. In regards to filters, we typically have sand, and now we have a plethora of geotextiles which can be used in this case. You should understand the organizational structure of the QA component, QC component. These are the stakeholders or the players, so to speak. You have an owner of the facility, a designer of the facility, the QA organization, which is typically separate. Then you have a permitting agency. It could be both state and federal. program manager and contractor, and then obviously the soils component as well. This EPA document shows this flow chart and the interactions of these different stakeholders. You see the initial portion of the curve here, and then subsequently the flow chart breaks into two paths, one with geosynthetics and the other with natural soils. It all has checks and balances associated with it, and all has approvals of the facility, both by the owner who pays for it and the subsequently regulation who finally approves it. These stakeholders typically have a minimum qualification associated with it. The designer typically has a PE license. The manufacturer has experience, and typically there's a given number of 1 million square meters of material produced. The installer has experience as well and might have a certification. MQC is typically ISO 9000. MQA, the regulations are typically silent in this regard, but we're seeing them being pressed a little more as far as CE marking. CQC, as far as construction quality control, this is IAGI certified. We're seeing the installers, and many in South America are having this IAGI certification. And as far as the CQA, PE or GCI ICP certification for the techs. You have to realize that the rules at a facility are governed by the plans and specifications. I can talk to you about minimum technology guidance and these suggestions that are made, but please realize quite apparently that the plans and specifications for a particular project govern how you're going to conduct yourself out there. They're typically prepared by the QA organization. The purpose is to supplement or augment the plans and specification. You present all the details in these documents, and it should be part of the permit process. The contractor and installer, as well as the QA firm, obviously, need to read this and review it before bidding on the project. There should be absolutely no surprises once the dirt starts flying or the polymers start flying. There is much documentation associated with this. Daily inspection reports, daily summary reports, inspection and testing report, any problems and corrective actions, drawings and records, photographs, final document certs, document control list, storage records, on and on. All of this is now being monitored by project managing scheduling software. Just like we're using remote and virtual ideas, this is paramount now in this business of construction quality assurance. You see people out there with laptops and iPads making these documents, and there's a whole cottage industry supporting that project management and scheduling. There are meetings associated with this, a pre-bid meeting, resolution, pre-construction and progress meeting. All of this, which I have just described to you, is freely available in that EPA 600 R-93 document, which is available online and will give you about 90% of what the ASC Koerner Daniel document gives you. So that's a brief introduction, just a view from 10,000 feet of what we're going to talk about in this presentation. I realize most of you that are on the line are very familiar with geosynthetics and containment systems. However, I would be remiss if I didn't go through it just a little bit to catch everybody up on the same page of what I'm talking about with these polymers used in below ground construction. Typically, the categories are membranes, GCLs, nets, textiles, grids, plastic pipe, and geocomposite. What I'm going to speak mainly to you about is the geomembrane, which is the polymeric barrier which is used in these containment systems. It can be smooth or textured. It can be scrim reinforced. It can be different colors. Most of them are black, but some of them are white, and we'll go through all of that. There is GCL, which is typically bentonite clay sandwiched in between two different geosynthetics. This clay swells profusely. It can absorb 300% moisture content, and it supplements or replaces a compacted clay liner and is used with the geomembrane as a composite liner system. You typically have geonets, or in Europe, they're called geospacers. These materials are three-dimensional, and they can transmit fluid, either gas or liquid, in the plane. They have a transmissivity associated with them. There's biplanar as well as triplanar nets, and it works well for leachate collection and removal systems, as well as detection systems. Probably the oldest of the geosynthetics are geotextiles, two major varieties, non-woven and woven materials. They can solve a plethora of different issues, and certainly are well received and well used throughout waste containment. Geogrids are three different types: punched and drawn, coated, which is typically polyester, and strap type. They almost always reinforce soil. Soils are notoriously poor in tension. Geogrids are excellent in tension. The composite of soils and geogrid can be equated to concrete and steel. Same scenario there. The geogrid, like steel, is taking the tensile forces. There are plastic pipe. This can be perforated or smooth. It can be corrugated. Typically, the pipes that are available are polyethylene, HDPE, and PVC. You then can have a composite of these materials, which are addressed, forming just the endless array of geocomposites. You should know the primary function. Here you see the different geosynthetic types that we went through. The primary functions of separation, reinforcement, filtration, drainage, and barrier. The geomembrane and GCLs will behave as a barrier. The net will behave as a drain. The textile can behave as many things, and it even could behave as a barrier if you shot it with a bitumen. Geogrid is reinforcement. Geopipe is drainage, and then obviously a geocomposite acts as all of them. This equation is how I would define an engineer. It's a factor of safety equation with a test property in the numerator. In the denominator, you have a design property. The test value is typically an ASTM or ISO test method, and the design value is typically, these days, a computer program. You have a testing issues. These are utilized through Committee D35 in ASTM or ISO TC 221. There's many standards which are available to you and essentially called out in specifications. As far as the design models, which are in the denominator of the factor of safety equation, they're utilizing geotechnical, hydraulic, and environmental engineering concepts. There's a litany of different programs that are available to you, and certainly there's some engineering judgment which has to be used not only in data entry, but also the analysis of this. When you go into a factor of safety, there are two critical elements associated with it. One is time, are these facilities temporary or permanent? And the other is severity, non-critical, critical. And I talk to people as far as criticality. Is somebody going to die over this? That's a good analogy for severity. You can see the factor of safety for these different functions varies considerably. Certainly when you get down to a barrier, I don't know how much leakage is allowed. Obviously, I gave you targets earlier on, but if you want to get better than those targets, certainly the factor of safety would go to the moon. In regards to generic specifications, the current thrust is to move towards this and uniformity. This is a major effort at our institute, and please realize on geosynthetic-institute.org, these specifications are available to you. I should point out to you that currently these specifications are being translated into Spanish. Certainly they can be translated into different languages around the world, and Portuguese might be next. The role of the QA personnel is certainly to observe and document. They're basically the owner's eyes out in the field. The consultants that provide these services are certainly trying to minimize potential liability, and they're providing documentation of what was built and did it conform to the plans and specifications. Good QA, though, is more than that. It leads to project success, and certainly it's an assistance to all the construction managers out on the project, and ultimately the owner think that it's a worthwhile expenditures. Okay, now moving on past geosynthetics, I want to get into the geomembranes. These are polymers. These polymers are characterized by molecular weights which are extremely high in the 10,000 to 100,000 range. You realize that geosynthetics use very few of these polymers, almost commodity polymers. The two materials up in the top are polyethylene and polypropylene. These are characterized as olefin plastics. We do see PVC and polyester used, but to a lesser extent than the olefin plastics. The chart above now is defining the polyethylenes a little bit clearer in regard to density. Mueller has presented this. Density is directly related to crystallinity. The more crystalline the material, the more chemically resistant the material. Also, the HDP has very little branching in its backbone. It's very resistant to chemicals, and it's why it's used in liner systems. Linear low density has a little bit more branching, but also has a little bit more flexibility, and that's why it's used in cover systems. Please realize I say HDPE, but this is a formulation. There's a recipe associated with this. The vast majority of the HDP or polyethylene is resin, 95 to 98%. This material does have carbon black and additives associated with it. These additives and carbon black are only in there a few percent, but they're the expensive part of the formulation and certainly needed to make these materials last a long time, even in harsh conditions. Here you see the polyethylene pellet, which typically arrails in rail cars or gaylords at a facility. You would like to mix the carbon black, but please realize these additives and the carbon black, the blocking agent, are typically in powdered form. Therefore, they're typically mixed with a carrier resin and form what's known as a concentrate. A manufacturer needs to assure that this material is quality material and conforms to his internal specs. He also wants to make sure, he or she wants to make sure that this material is good material and what he paid for. So typically the quality assurance before the manufacturer will release this material into his silos at the plant is twofold. One is melt flow index and the other is density. They'll do these cursory checks to make sure the material is quality and what they're paying for. Now we'd like to produce that geomembrane. And to produce that geomembrane, you typically have extrusion processes or calendaring processes. The olefin plastics that we showed you are the extrusion, flat die and blown film, and we'll show you both of that. As far as the calendaring process are concerned, that's typically PVC and also the scrim reinforced materials. So we take the resin and the concentrate, which is the carrier resin, and the additive package and the carbon black, and then we have to make sure that we address regrind or rework. This is allowed at 10% into the letdown. And this is important, especially from a financial perspective for the manufacturer of geomembranes. However, this material has never seen use. It is most often has never left the factory. This is quite a bit different than recycled material or reclaimed material. Absolutely no post-consumer material is allowed in geomembrane manufacturing. This is strictly forbidden, even if it goes through a pelletizer and a washing mill. It's tough to detect, but certainly the formulation has to be guarded and protected against this. Now we'd like to introduce that letdown and regrind into the extruder. That extruder is basically a large Archimedes screw with heaters on the side of it. It then feeds a die. In this particular case, it's feeding a wide mouth die. This die lip is about 10 meters across, so it's a very large die. It can be fed by multiple extruders and is spread out quite wide. Here you see the river of polymer, the river of geomembrane that's being produced. It's on the cooling rack after the calendaring. This is very different from blown film extruding. Now the die lip is circular. We're looking down on it. The geomembrane is orange. It's just for a contrasting color. It's nice pictures to take. And now what we're doing is looking up at it. So the die is base here. It's a circular die, and the nip rollers at the top of the facility are here. So two very different manufacturing processes. You can add secondary and tertiary extruders to this for nitrogen expulsion or different colors. Here you had a different color inside, white. At the top of the nip rollers, it was slid open and then splayed forth to go on a roll-up wheel. These rolls are heavy after they're manufactured. You typically have dedicated slings associated with them, and this has to be moved around and labeled quite well. It's typically labeled on the outer wrap of the roll and also in the tube of the material. All of this is specified by the QA plan. As far as texturing material, you have 4 different methods to texture. For blown film, it's typically a nitrogen expulsion. For you can have a patterned roller for the die cast. Hot particle impingement. I've seen that in Chile as well as China and Europe as well. Hot foam lamination I see less and less of. That was a favorite of a manufacturer here in the United States, but we see less of that process. The texturing is key for increasing the frictional interaction of the surface. Here you see the blown film in the upper diagram, and here you see a patterned texturing process. This has revolutionized the industry, particularly on steep slopes. You can have slopes now much steeper than 3-to-1. We see 2-to-1 on a norm, and this is obtained with textured geomembrane. Okay, I showed you a perfect world in those photographs. There are problems which are associated with the manufacturing of geomembrane, and certainly the QA personnel have to pick up on this. Things that are out there, I won't show you all of them, but when an imperfection like this occurs, you have to establish, is this a defect or is it a blemish? The difference in definition of this is a defect is something that does not cue into the specification. Values fall below the specification values. Obviously, in this case, if you would run a tensile test or a thickness test, this is much more than a blemish. It would certainly be a defect. In regards to textured material, if you're not cleaning the die lip, you can have excess material, which can agglomerate on the texturing surface and give problems. You can have gels or dirt inside this. The screen is not working well with inside the extruder, and these foreign materials enter the sheet, which give problems and rise to stress cracking. You can have problems with carbon black dispersion. These big carbon black agglomerates are problematic and certainly need to be taken care of. If you have water with a lot of humidity or a problem with water dripping on the equipment, it can bubble the material and cause problems. You also have startup runs, which are between different materials, changing over from linear low density to high density, or changing in thickness. There could be startup issues. You don't want this material on your site. There could be problems with AO packages, which are found out in long-term problems. There could be problems with inconsistency or tiger striping of the material. Certainly, you didn't pay for this. This was not the material shipped for direct shear testing, and certainly is problematic and should be avoided. Realize that there are specifications. These specifications are typically generic, which are the best specifications. You don't want specifications from a manufacturer. It's not that they aren't honest, but it's like the fox looking after the hen house. You need somebody independent producing these specifications. They typically address properties, test methods, units, limiting values, frequency, and then there's a warranty. There are generic specifications available to you. Our geosyntheticinstitute.org provides them. They're openly available to you, and as I said, they're being converted into Spanish now and hopefully other languages going forward. The test methods that are called out in these specifications should be tested by a manufacturer who's accredited, and also by a third-party laboratory which is accredited as well. They should be accredited to ISO 17025. Certification, there is CE marking, which is available particularly in Europe, but I see them all over the world. And also certification of the personnel which are looking after the site, as far as experience, referencing, knowledge, they pass a test, and then continuing education. It's available to you. It's a very organized system. And certainly this has been set forth by the US EPA, and hopefully it will take hold throughout the world. Okay, now we've manufactured the material and we'd like to ship it to the site. This is typically done in enclosed trailers or flatbed trailers. It depends on the equipment for loading and unloading. I should point out to you that the QA sampling is best done at the plant. Transportation costs has become extremely expensive, and certainly we need to head this off, problems with this as soon as possible. That testing is typically the responsibility of the manufacturer, and the test occurs prior to shipping so that you can inventory and hold any material that is off spec. QA sampling in the field is certainly not as efficient, but sometimes it's called for. Please realize that a failure, if the QA sampling is done in the field, will delay the project significantly. And maybe the manufacturer doesn't have material inventoried that he can ship directly to the site. Who pays for the shipping back and forth? This has to be arrived at earlier on in the project. As far as the shipping is concerned, this is typically with organized equipment in the manufacturing facility. Here you see it's done with a stinger. This is offloaded typically with a low and a spreader bar. This is a low boy, and this is in regards to a container vessel. Storage requirements on site. The site must be suitably prepared, and especially should be at a high point with no standing water. The position of this storage facility, you should arrange the yards so that you have easy access, and so that it's very close to your work. You don't want to be taking these materials for a ride, for a long ride. It wants to be staged next to your installation crew, ready to be moved on site. If the storage on the site is greater than 6 months, you should cover this material with some sort of shelter. These are typically covered pallets, tents, canopies, or containers. I'm seeing this a lot more often. Owners are buying large quantities of geomembranes and storing them on site for extended periods of time. This is no problem, but certainly they have to be stored properly and sheltered if it's over a 6-month period. In the upper photographs, you see good storage. These are high and dry on a sacrificial piece of geomembrane. The geotextile is covered, it's in wraps, and it's on pipe, which is off the ground. Below is very poor. Here you see weeds growing through a geonet. This is going to be very problematic to install, telescoping rolls, and a lot of dust and dirt associated with this. Here's an extreme of uneven surface, water, and certainly telescoping of the materials. You've compromised the geomembrane, and certainly it's a bad way to store materials on site, even for a short period of time. As far as field placement of the geomembrane is concerned, you have to prepare the subgrade. You have to follow the QA documents, follow the lines and grades. It has to be stone free and flat. If you're in the winter time or near winter, in the late fall or early spring, you should have no frozen ruts. Tire deformation should be less than 25 millimeters. Nothing can be greater than 25 millimeters. Remove folds in any underlying geosynthetic, and then subsequently get a subgrade acceptance letter. This is something that the QA personnel needs to obtain from the earthwork contractor, and that has to be signed off by the owner. To do this, you start off with a site which could have some bony material, some greater than 25 millimeter size material. This material need to be picked out. You can do that automatically with a stone picker or by hand. Please don't throw these laborers should have a bucket. They shouldn't be throwing the particles on deployed geosynthetics, obviously. You then take a smooth drum vibratory roller and roll the site flat. This is to make the material, the compacted clay liner, ready to receive the geosynthetics. This is a photograph that I took at a site, and the owner asked me if this was appropriate. I said, absolutely not. You can see where the material is near being punctured. You can see where the material around the batten strip is under tension. You can see a lot of down drag forces by the pipe boots. This is totally unacceptable, and this geomembrane will be compromised over time significantly. It's an unacceptable way to install a geomembrane. You will have to protect the geomembrane when backfilling. Punctures by stones from both above and below are problematic. Cover soil must be free of stones. If possible, the gravel leachate collection and removal system has to be separated from the geomembrane with a heavy needle punch non-woven or a puncture protection material. Geomembrane also cannot be trafficked by construction vehicles. There is some discussion around low ground pressure ATVs. This has to be agreed on, though, prior to the job. The ATV typically has special precautions, like entering the geosynthetic at a 90-degree angle, no fast starts, no on-off the geosynthetic. It has to remain on there. In addition to that, if the material is to be trafficked, it should have a minimum thickness of cover soil over top of it. That's typically greater than 300 millimeters or 12 inches. Some regulatory agencies, like the Corps of Engineers, want 150 millimeters or 18 inches. But all of this is specified in the QA documents, the QA plans. In regards to top side of the facility, pardon me, the anchor trench detail is extremely important. This anchor trench is holding the geosynthetics topside. It has to be detailed in the plans and specification, and it's critical for safety, particularly when you get greater than a 3-to-1 slope or greater than a 30-meter slope in length, 100 feet. If you do not tie off or backfill the anchor trench, you could have issues with wrinkling or caterpillaring of the geosynthetic downslope. You should backfill this per the design, and please don't use the anchor trench as a trash can. This is absurd when you see a lot of different materials, even spent sandbags in the anchor trench. This all has to be removed and take care of in a very diligent way, obviously not to pollute the environment. You should assure that the anchor trench is dry and is drained. We have tremendous weather that moves into locations around the United States. This anchor trench cannot be flooded. The pull-out resistance in a flooded anchor trench is much different than it is in an anchor trench that's been backfilled and very well designed. With this anchor trench, you also have to make sure, is it a compound anchor trench or is it a solo anchor trench? A compound anchor trench will receive many different geosynthetics. In addition to that, the anticipated liner cover tie-in. Some facilities have a cover geomembrane tying into a liner geomembrane to totally envelop the waste. If this is not done properly, it certainly will be an installation headache. As far as installation, there certainly needs to be a right way and a wrong way to do it. This slide demonstrates two very wrong things to do. Here, the installation contractor does not have the proper equipment. These forks can certainly gouge the geosynthetics and cause damage to the outer wraps. Who pays for that? The installation contractor certainly pays for that, and the owner will bring that to attention quite readily. As far as this is concerned, this is a dangerous scenario. This is a smooth geomembrane. The roll is extremely heavy, and they're about to throw it down the side slope in a very uncontrolled manner. This is totally unacceptable and certainly is not the way to do it. Good delivery systems are shown here. This is typically equipment, a lull with a articulating boom and a spreader bar. This is equipment which is operated remotely. There's a toggle which the installer is here walking in back, making sure the overlap is correct. But this is certainly carefully managed and controlled throughout the system. You are helped tremendously in the installation by a good design. And what I mean by that are typically long longitudinal cells. Here you see it in schematic. You also see it here. These systems become complex. Here is a composite liner system of a GCL in gray, a geomembrane in white with black edges. This sheet is a rub sheet, and it's textured geomembrane, so it would bite into the needle punch nonwoven significantly. They're going to deploy the geomembrane and then pull this rub sheet out like a Houdini trick on a tablecloth. So you need to know the installation procedure and certainly have to be cognizant of it going forward if you want to be expeditious on your installation. You should address extreme weather. I mean, extremely hot or extremely cold weather. There are recommendations in the EPA guidance documents, which I talked to you about. These EPA recommendations give you trepidation once you get colder than 0 degrees C. So at the threshold is certainly at freezing. Special precautions for lower temperatures. You can seam at lower temperatures, but certainly you need to take precautions. Those precautions include preheating, moving enclosure, and certainly the QA plans need to be specific in that regard. There is direction both in IAGI as well as GRI GM9, which addresses these extreme conditions. In most cases, though, the QA personnel will have to consider extra trial seams. This is very important and certainly is at the prerogative of the QA personnel. I have been talking to you mostly about olefin deployment, either polypropylene or polyethylene, you should realize that PVC often arrives at the site in palletized form, much larger panels, and it's typically accordion folded and is deployed in this manner. Off of the pallet, they back up, and then a lot of labor is required to spread the sheet flat. You do run into this predicament, particularly with surface impoundments. This is problematic in regards to the subgrade soil. The subgrade soil had much organics in it. Upon putting a black body over top of it, gas came out, or gas was expelled due to changing water table elevation, and ballooned underneath the geomembrane in regards to whales and sometimes called hippos. To alleviate that, you would need gas venting systems. You see two gas venting systems here. The one on the left-hand side for a landfill gas vent, which is sort of a candy cane, and on the right-hand side, a flap vent, which is used in tandem typically with a needle punch non-woven or a geocomposite to drain the gas. Field placement of the geomembrane, typically there's a positioning or spotting, which is important. You should certainly minimize subgrade disturbance. There is a concern with textured sheet. I showed you the rub sheet or Houdini trick, which is often used. There's also a concern with wind. These materials, you do not want them to be a kite. Many cases of wind displacement. The biggest item is not to leave the geosynthetic exposed too long. It should be managed or staged construction. And certainly, what do you do when the material is damaged? Here is the case, and certainly what is the prognosis of the geosynthetic? The geomembrane has been abraded, bent, might even be torn. The truck on top of it certainly hasn't served it well. Can you use that geomembrane? How many defects are you going to allow in a panel to still use this material? Do you not have enough material on site that has to be used in the place of this material? Please realize these contingencies all need to be discussed before they occur. You don't want to be arguing about this after the fact. Problems of exposed material are certainly wind, expansion or waves, accidental damage, intentional vandalism, or birds and seagulls. Here you see nature playing a dirty trick on us. The membrane exposed, and certainly all this material will need to be cleaned off before the drainage layer could be placed over top of it. There is a situation in regards to waves and wrinkles. Please realize most liners which are placed are composite liner systems of a membrane being placed over top of clay or a GCL. You can't entomb these waves because you will not have intimate contact. These waves or wrinkles fix into position, and certainly is a concern with residual stress and mini dams. There's excellent work that has been conducted on this. I point you in the direction of Tiang Song's work with Bob Koerner. There's also work at Queen's University with Professor Rowe and Brockman at the Quelts up in Queens, which are very good in regards to this work. This is what we're talking about, waves and wrinkles. This one here in the lower picture is massive and certainly will not dissipate over time. Three situations which I present to you. One, a compacted clay liner alone. The reason you're using composite liner systems is that wetting front is much decreased if you get a hole in a geomembrane over top of a GCL. If you have, though, a hole at a wrinkle or a wave, this fluid can move in the Z direction in and out of the board in an entombed wave and radically change the leakage rate at your facility. So ultimately, you would like a press fit of the geomembrane against the underlying clay. This occurs in all geomembrane types. Waves accumulate in stiff, thick geomembranes the most. They occur in flexible membranes, but they're smaller, but more numerous. They're very obvious in all the polyethylenes, both HDPE and linear low density, and entombing these waves are problematic. You have to be very careful when you're covering this material, particularly with leachate collection and removal stone. The QA personnel is making sure this is flat. In this particular case, the wave is getting too long. It needs to be cut out and flattened, or you have to wait until a cooler period of the day until you continue this covering. You might want to stage this work incrementally so you get distributions of the wave. There's a right way to do this and a wrong way, and certainly you need a press fit of the geomembrane against the underlying material. Concern over entombed waves is certainly lack of intimate contact, which we described the theory. Many dams which are forming and with sites that have limited hydraulic gradient thresholds, this is problematic. Stress concentration is problematic, and also a distortion of the underlying clay or GCLs. It's one thing to present a problem. It's another thing also to give solutions to this. Bob Koerner very nicely put this table together and the way to solve the problems. Certainly that push, accumulate, cut, and seam, it's labor intensive, but it works. Fixing berms and piles. This is available over in Europe. A company by the name of Schicketanz has certainly championed this with thick geomembranes in Germany and Austria. White sheet and white and light colored geotextiles help. If you decrease the surface temperature of these membranes, you certainly have less wrinkling. If you can control the environment either with tenning or support structures, or do work in the morning or late at night, this is certainly proactive and will help you in regards to intimate contact, which is extremely important. Okay, now we're moving on to seaming and joining of these geomembranes. Leaks do occur due to poor field seams. Factory seams are much better. Details around penetrations are certainly very important and around appurtenances. The crew must be well trained, and there is a requirement that in some places that they're certified. The equipment must be maintained and is certainly tracked. These expert systems track both the operator and the equipment that they're using. In regards to the area to be bonded of the geomembrane, it must be clean and it must be dry. These are two very important factors, and it certainly is absolute. Here you see the cleaning and the drying associated with it. There are manufacturers that do have Teflon white strips, which are pulled off right in advance of seaming. There are heaters like salamanders would heat the location, or cases where you're wiping a location free. Most of the membranes which we see, even textured membranes, have a smooth edge, and this is good for seam quality. Tie-in seams are quite ugly. This issue of tying in one cell to another, this is an active cell which is filled. This is a cell that's being prepared next door to receive waste. The berm separates this, and now to tie in these old geosynthetics to one another is problematic. You sometimes see a lot of elaborate protection systems. It can be with plywood or other geosynthetics which are pulled up in advance of the seaming, but certainly should be thought about with great care. As far as the seaming methods occur, it's very dependent on the type of materials which are used. The olefin plastics, which we described, are seamed thermally, either through extrusion or fusion welding. Fusion can be done off of a wedge or hot air. Chemical seaming with solvents or bodied solvents are done with PVC and chlorosulfonated polyethylene. Adhesives are typically used with EPDM. Solvent seaming and adhesive seaming we don't see much of these days. Even PVC can be thermally seamed, although this is available to you, and we see it often in the roofing business, but not so often in the field business except with EPDM. Applicability of seaming methods. You see here the different methods versus the different materials, what's available and what's not applicable. This is developed again by Koerner, Daniel, and Richardson, and we're pretty much going to speak to just the thermal methods of seaming olefin plastics from here out. There is a genesis of seaming of these materials. You see large flat extrusion, handheld extrusion, single wedge, and then double wedge material, which is available. Wedge welding, typically with 2 tracks with an air channel in between, is the norm. This air channel is a non-destructive test, which is built right into the material. It's certainly the premier technique for production seaming, and it is highly automated and certainly is the best type of seaming that we see out in the field. This is the original patent from Pfaff, which was an Austrian firm. This is granted back in 1979. The big component of it was a Z-type frame with a movable wedge. You see the seamer here with a split nip roller, and the wedge is a brass wedge. The lower sheet is placed, the wedges move forward, the upper wedge is placed, and then the device is racked or moved to apply a normal pressure. There are many different manufacturers of this equipment out there. You do have to qualify the integrity of the seam as well as the integrity of the seamer or the installer. In this slide here, we're making sure the overlap is correct. It's typically in the neighborhood of 100 millimeters so that the seam can be applied properly. Very different between longitudinal and butt seams. The butt seams on the roll edges are typically done with flat, solid wedges, where the longitudinal seams are done with split wedges with DualTrack hot wedge seaming. A single wedge seam is shown here. You see the area that's bonded plus the squeeze out. Here you see an indication, 2 indications, and a schematic of a DualTrack hot wedge seam. In between is the air channel. You can't have the air channel closed down by squeeze out, so it has to be opened and free for the test. There is a lot of new seamers that are available out there. These are now fully automated hot wedge welders. This automated welder or smart welder can record temperature, speed, and pressure. Any anomaly to this can be recorded, and then the QA personnel can focus on those locations where these metrics are not within threshold. That's wedge welding, very different fusion welding than extrusion welding. This is certainly not recommended for production. There's a lot more opportunity for human error, but it's used on every site for patching and repairs. So regardless, it's certainly important, and you need to deal with it. It's a labor-intensive process, typically of tack welding the material, then grinding the surface bloom off the material. You will use an extrusion host rod that's fed into the machine, and you have to cover over all the grinding of the material. This is what it looks like on site. Again, back-breaking work, but certainly necessary for any repairs on site or details. The extrusion bead flows over a Teflon shoe and certainly smooth. The location of that bead is extremely important, and you should maximize this distance here for the extrusion bead. In this particular case, it's a white extrusion bead. Maximizing that distance is critically important for a good seam. You are covering all the material that's been ground away, and certainly the 2 times during the day, you are going to check the equipment as well as the installation personnel in regards to a trial seam. This trial seam is typically done in the morning and then after the lunchtime or the noon break. It's used to qualify the seamer and their equipment. It's made on excess scraps of geomembrane and typically should be done on the subgrade soil or the geosynthetic which you're installing. It should be tested immediately in the field with a field tensiometer. If it passes, you can go into production seaming. If it's no good, you get a retrial. If it's still no good, they need to go through retraining and repair or maintenance of the equipment. This is very important that all of this is tracked, and important to see that its records are kept throughout the project. This is the work that's done with trial seams. There's a field cutter and a field tensiometer. That field tensiometer is typically in a job trailer with climate control so that you get a good response. This is very different than destructive seam testing, which is typically 1 in 500. We'll talk about this later in the presentation, but please realize trial seams are very different than destructive seams. The location of the destructive seam is extremely important. You will want to cooperate with the installer and put this destructive seams in above the water line or above the leachate line. You can imagine this destructive patch, which is being placed on a vertical wall here in the lower picture, is very problematic to the site. It would be much more beneficial if they would place it upslope away from the liquid level. Cutting 1 meter holes in the site is going to take out 1 meter of wedge weld, and it's going to be replaced by 3 meters of extrusion weld. And what I showed you earlier is that the fusion weld or the wedge weld is much superior than the extrusion weld for this case. To give you an idea of assessing this and to assess the integrity, GRI has produced 3 different practices. It's GRI GM 29, which gives sort of a carrot and stick approach to expanding the paradigm of 1 in 500 feet for the destructive seams. There's a method of attributes, which is GM 14, and control charting, which is GM 20, to reward good installation and to open up that spacing for destructive test. As far as destructive test, these seams are not tested in the field. They're typically sent to a third-party laboratory, which is off-site. It's usually Federal Express or DHL to the site, and then tested in regards to shear and peel to determine the adequate bonding of the material. It's typically 5 replicates in shear, 5 in peel. They're alternated as you see in the picture. There's typically a clicker press with a gang die, which produces these materials. It's then tested in shear and peel. Requirements are called out in GRI GM 19A and 19B for chemical fusion. You're using ASTM 6392 or 6214 for these materials. And typically the laboratories are conducting this on 5 station units, as you see here. As far as the peel testing is concerned, we're looking at peel adhesion of the material. And this is a measure of pulling the materials apart with 2 flaps. You're looking for 3 properties: a peel strength, a peel incursion or separation, and then a locus of break in this case. Here you see it's set up in a continuous rate of extension. We're now pulling this typically at 50 millimeters per minute, and then have a ductile failure of the material. This is very different than the shear testing of the material. This is the type of stress that the material would see in the field. You again are looking at 25 millimeter wide specimens. You're testing them and looking for a shear strength, an elongation at rupture, which have to be greater than 50% typically, and then a locus of break indication in that regard. Here you see the shear test set up. We're pulling, and here in the bottom you see a yield of the material. The bond was stronger than the material, which is a good indication. Again, a ductile failure, you'll see those fibrils of the material, and this is a very successful test. Seam acceptance criteria, like I said, is based on GRI GM 19A or B. They're available on our website. You're always looking for a film tear bond, which is a ductile break where the sheet fails and the seam does not. You're looking for minimum delamination, particularly in peel, and then the seam strength, the shear is 80 to 95% of the sheet strength, the as received sheet strength. The peel strength is anywhere between 40 to 62% of that strength. Okay, that's destructive testing. Now let's take a look at non-destructive testing, which is certainly a considerable activity on site for the QA personnel. I told you that the Fusion DualTrack hot wedge seam was the premier method for seaming, and it's also the premier test for evaluating the seam. All geomembranes can be seamed in this manner, and certainly there are numerous alternatives for non-destructive testing. The one most basic, and particularly that's done for solvent seaming, is air lance testing. This is jettisoning high pressure air through a nozzle, and what you're looking for is a flapping or unbond. This is done typically on scrim reinforced materials or PVCs. I never see it being done on olefins except for very thin polypropylenes. The DualTrack air test is certainly the premier test. You've seen this cross section before, and that air channel is very important to the success of this test, and it certainly needs to be open and clear. You need to isolate the air channel, and you do that by closing off the two ends. That's typically done with hot air, Leicester seam, and wide mouth vice grips. You then will insert an inflation needle into the air channel. There are many different needles and apparatuses which are used for this. You certainly need a good seal, and you can't have a leak in this regard. You then inflate this with a pump, and then disconnect the pump at the start of the test. As far as the test is concerned, the criteria is set forth with GRI GM6 for air channel testing, the specification. The specifications are based on geomembrane type, thickness, minimum and maximum pressures that are associated with those types and thicknesses, a pressure drop over a given time. And all of this is called out in the standard. What you don't want to see are these aneurysms in the air channel test. This in regards is poor seaming, or indicates poor seaming, and certainly is what the QA is after. Documentation of this, again, is in an expert system. You see the recording of this in picture form from a site. It's typically a date, the pressure before, the pressure after, the hold time, and the time and temperature, and then the sign off of this. A lot of photographs are being introduced into QA records. This is certainly very important, and in this day and age of expert systems and iPads on the project, certainly readily available. Another non-destructive test is a vacuum test, for extrusion welds. This is probably the oldest. It's an adaptation from the roofing industry. It's very labor intensive, and it's typically requires a soap solution put down on the geomembrane and then the vacuum box placed over top of it. You engage the vacuum, and what you're looking for is bubbling of that soap solution to indicate a leak. Bob Koerner and Greg Richardson produced a very nice paper back in the late 1980s. They summarized it with this table of non-destructive tests, general comments in regards to it. I'd point you in this direction. It's a separate document from the R-93-600, but again, available through the US EPA, and I think heavily advisable. With all that said, in regards to the non-destructive testing, you should note that the current trend in our industry is to use electrical leak testing of entire systems. It focuses not only on the seams, but on the sheet material as well. And it also can detect leaks after backfilling, which is extremely valuable. There are a bunch of methods which are available to us. It's focused on the completed system just prior to commissioning the facility. And in truth, these tests, which I'm going to describe very quickly, are system performance tests, which are quite handsome and quite well received in our industry. The concept of electrical leak testing is typically to use a DC power supply. You have a cathode, which is grounded beneath the liner system, and then typically a movable anode, which is either in the liquid or wet soil above. You're aided by a voltage indicator, and certainly there are many variations to this. You can do this with water. You can do that with either puddle or standing water. You can do this on soil which had been wetted. You can do this with conductive geomembranes or geotextiles in many cases. What you're basically doing is fishing with electricity. And what you'd like to see whenever there's a hole is there'll be a flip-flop in the voltage. This is particularly the case with the two dipole methods, either water-covered or soil-covered. The water-covered is certainly the premier technique where you can find the smallest holes. There's a lot of activity in this regard. TRI, I have to give them a shout-out. A woman by the name of Abigail Beck-Gilson has been working these standards through ASTM with a lot of help from others. Methods of electrical leak testing are shown here. The water puddled, the dipole method, conductive back geomembrane, water lance, conductive textile, blind leak assessment, arc testing, and then a practice for mapping the leaks. This is certainly about 15 years of work. We have a lot of experience now throughout the world in this. It works quite well, and it certainly has come of age. Comparison of leak testing, sort of the pros and cons. Again, this is Bob Koerner's work back in 2001. He gives advantages and disadvantages for each one of these. You can read this yourself, but I can tell you that this is a tremendous success, and some states within the United States are mandating this prior to commissioning facilities. Okay, so that's about an hour of 15 minutes, an hour, 20 minutes of straight talking. If you would prepare your questions, this is certainly the time for it. In summary and conclusions, I would like to tell you that geosynthetics work very well as barrier systems, but they're tricky. They need special care in their installation. I suggest, and what's been suggested, put forth by the US EPA and certainly many countries around the world, is a system approach to good facilities. This system approach has a good design with a registered PE stamp. It's using quality materials, materials like GM13 or GM17 materials. Accredited test labs, both in the manufacturing facilities and the third-party laboratories, according to ISO 17025. The best available installation, this could be IAGI installers or certified installers, but certainly they're trained and they're using good installation equipment. You have quality assurance, typically by a third-party facility consultant. This quality assurance could be certified. It's certainly important to be well-trained and knowledgeable. You don't want your quality assurance personnel learning on the job for the first time. They certainly should be knowledgeable and have experience, and that knowledge has to be checked. As far as proof testing prior to commissioning, the non-destructive test of electrical leak location is certainly what we're thinking of here. Very important and certainly worthwhile. These facilities are going to last in the form of covers 30 to hundreds of years. Certainly careful operation and maintenance of these facilities are important. They also could be monitored. This is certainly the system approach, which was set forth by the US EPA and certainly is encouraged whenever you're using geomembranes and geosynthetic containment facilities. I'd like to acknowledge the sponsorship and support of the consortium of the Geosynthetic Institute. This is our location. We're available to you to service the industry. Thank you so much for listening, and certainly I'll take your questions. If you have questions that you think about that are not immediate, please don't hesitate to reach out to me. My email address, gsigeokerner@gmail.com. Visit us on the web, our website there. I also answer all the GMA tech line for IFAI. You can get me at many different vehicles as you see here. Okay, now it's time for your questions, and certainly Benjamin will give us the questions. Thank you so much.
Thank you very much, Dr. Koerner. That was a very good presentation. We have a lot of questions here from different parts of the world. So I will respect the order of the questions, but I will make the first one from one of the pioneers of geosynthetics here in Brazil, that is Professor Enio Palmeira. His question is...
He's in there. I wish I was with him. It would have been so nice. Oh, I was sitting at a table with them a couple of years ago. How are you? It's not time for that.
That's why I did his first question.
Oh, man, from Oxford. So nice that you're on.
So basically, his question is, only American laboratories can be accredited for geosynthetic testing in the US, or foreign laboratories can also be accredited?
Yeah, there currently is 111 laboratories in the GAI lab program with 21 countries around the world which have been accredited. We're now virtually accrediting laboratories. I'm not comfortable with this. I'm a people person, but this is a worldwide program which is available.
The next question is from Antonia Byrne. I believe she's from Panama. What does GM13 standard means when considering by a HDPE geomembrane?
So the GRI GM13 is a generic specification which is older than 15 years now. It covers both smooth and textured geomembranes, and it goes from 0.75 millimeters up to 2.5 millimeters in thickness. This specification is available internationally online. It's certainly a generic specification, and it's broken down into 4 parts: physical, mechanical, hydraulic, and endurance properties. We feel very strongly that this needs to be a high quality material, but materials that conform to GRI GM 13 are good quality materials.
Professor Enio Palmeira is sending his best regards here.
Oh, you make me smile. It's so nice to hear from friends.
So people make a great confusion about GM13, about the frequency of the tests. They think that they should require this as they receive the material at the construction. Do you have any frequency that you recommend to test for the receiving of the material in the construction?
There are 2 very different requirements. One is the requirement from manufacturing quality control. The frequency is specified within the GRI GM 13 table. It's given the frequency and it's been agreed upon by the manufacturers of membranes. For conformance testing on the job site, this is a different entity, and the frequency of that is called out in the plan specification and QA manual. It's typically not all of the test. It's typically thickness, for instance. It's typically carbon black content. It's typically a tensile test and a tear test. So conformance testing, fewer tests and less frequent once it's passed manufacturing quality control. Done by 2 different entities.
We have another question from Victor Pimentel. How can the presence of post-consumer recycled resin on the formulation affect the durability and or the performance of HGPE geomembranes?
Okay, a very good question. There's 2 major concerns. The one is there's no traceability of the formulation. The second big concern is that there is degradation of the material, so zones of imperfect material in the matrix of the total sheet. Unfortunately, the geomembrane is only as good as its weakest link, and therefore it becomes problematic if this is discovered at a later date. It could be found out in regards to stress cracking. It could be found out in regards to stress concentration of the material. It could be discovered in many ways, but certainly that is not a risk to take in premium GM13 material. If the material is downgraded and used for a less critical application, so be it. But it certainly should not be GM13 or GM17 material.
Continuing this question, I watched your presentation a couple of years ago in Munich about calcium carbonate and how they can affect the behavior of the geomembrane in long term. Can you identify if in the composition of the geomembrane you have calcium carbonate or not?
Yes, you can. You can find out in 2 ways: by a carbon black content or an ash content of the material. You'll see that quite readily. Or you can also see it in the carbon black dispersion test. The material will sparkle once you take it. Unfortunately, talc or calcium carbonate gives some very good short-term properties to the material. Strength, and it also gives short-term tear and puncture improvements. Unfortunately, long-term, this is not so good.
Okay. Another question I can't read. I imagine it's in Chinese, the name, but the question is in English. Regarding field testing, how important is to do the field tests as exactly 2 inch minimum and 21 plus minus 2 degrees Celsius. Contractors always want to do it at the field site temperature as fast as possible.
Oh, this is a talented person who asked this. This is a real world question. So this trial seam, which is done in the field, typically it's done on a field tensiometer. Ideally, that field tensiometer would like to be placed in a job trailer with a controlled environment. How important it is to obtain this 21 plus or minus 2 degrees C. Really, it's important that the sheet reaches temperature equilibrium. So it's important that the sheet gets to that temperature. It can probably get to that temperature within 10 to 15 minutes after seaming if it's not placed in the sun. So it's important that it gets that temperature. There is a beautiful paper that is written in regards to temperature effects on the mechanical properties of geosynthetics. Higher the temperature, the lower the strength. Some installers will drop the bones in ice water to cool it down rapidly. This should not be allowed. You can cool it in an air-conditioned room, but dropping it in ice water will lead to amorphous region being developed, and is sort of a way to cheat. So the answer directly to his or her question, is you should get it to 21 plus or minus 2 degrees C. You can do that quite readily in about 10 to 15 minutes, and then test in a peel test. Having it hot will give you lower strengths. Having it cold will give you higher strengths. And the paper that I referenced is where you should turn to how much will that factor into account. Great question.
Antonia Byrne has another question about tie-ins. What will be the best way to tie one cell to the other?
This is a good question. What's typically done, or what we see done, is a special fusion welder. This special fusion welder typically has a solid wedge. It does not have a double wedge associated with it. So this solid wedge is run very slow. All of the overlaps are cut back, and at each of the overlaps, they make what is known as a T-seam. So this is extremely important. The second part that needs to be addressed is butt seams, especially when you're using material, remnants of material rolls. It's very important, if you're allowing roll remnants, try to get the butt seams away from the toe of the slope. Try to get them staggered so that they do not create a zipper. And again, take caution with the butt seams and use the solid wedge with a T extrudate on each end. Great question.
One question here from
this course, which I gave to you, is usually taught over a half a day. So I couldn't, I'm sorry, I short-sheeted you on this.
No, but that was amazing how many information could you give in 1 hour and 15 minutes. There's a question from Daniel Meucci. How do we evaluate seams between a GPE and LLGPE geomembranes?
Oh, neoplastic. You're another person. I wish I was with him too. He's a good guy. This is a great question.
Which just finish. Which value should we consider from GRI GM19?
Okay, so you're making the envelope transition with the linear low density and the HDPE. Typically, the linear low density is 1 mil, where the liner is typically 2 mil, let's say, 2 millimeters. You need to take the linear low density material and at the thinner millage. That should be the maximum that you should you need. You asked a question that I'm smiling at because I just I wrote the geosynthetic news column for Geosynthetic magazine. Your question will appear in the magazine next month. So Danielle asked a great question. I wish I was with him. He's a gentleman. He's a nice guy.
We have another question from Humberto Ivan from Peru. In contact with
Him too.
he's a good friend. Between both geomembranes, which one do you consider using in contactive soils, and which one would be the most appropriate to use in carbonate rocks?
Okay, there's a big issue in regards to carbonate rock from a pH value. This is not problematic for many monolithic materials. It is problematic when you get to scrim reinforced materials, which are reinforced with a polyester scrim. So I would avoid that from the perspective of hydrolysis. You could go to an amide scrim, which is a nylon, but I'd certainly stay away, or at least flood coat the edges so you don't have problems. The olefins, all of them, the polypropylene, linear low, and HDPE should have no problems in regards to alkali. They're used in containment systems throughout the world with, in this application, particularly with high alkaline phosphate mining and things like that. So it should be no problem whatsoever.
Okay. We have a lot of geomembranes, PVC, AGPE, reinforced AGPE. At the same time, we have two different geotextiles here in Brazil, polyester and polypropylene. I did a provocation to you 2 years ago because the specification of GRI says that can be both for polypropylene and polyester, but the behavior of both of them are pretty different. How do you handle that? Because people read the specification, say, okay, it's the same for polyester and polypropylene, so I can use the polyester in this environmental construction, and actually they can't. So
you have to realize when you create a generic specification, it's a process of compromise. You sense you're almost a politician rather than a scientist. You get the best you can. You try to make these generic. I think people are getting educated, and that they know the difference between these basic polymers. They know what behaves well and what does not. They also know the economy of it. Polyester at a 1.2, 1.3 grams per square meter versus an olefin, which has a 0.94 grams per square meter. You're going to have a different laydown of the material. You get a lot more for your money with the olefin. So the technical requirement as well as the monetary is going to come into play significantly. And again, you should educate yourself in regards to the applicability of these different materials.
Okay, thank you. Another question from Paulo Rocha about GM30 woven coated geomembranes. In your opinion, in what applications these materials are indicated, and how do you see the expansion of their use as prefabricated panels?
Yeah, this material has come on strong lately. It's available in India as well as in manufactured in the U.S. It's made in membrane form in 1.5 millimeter and greater. It also is made in a very light barrier form, which is about half that thickness. used as tarp materials. These materials really have made inroads for small facilities. In the oil and gas business in the United States, these facilities in the neighborhood of a hectare pond in area and things like that. It's they're drop-in materials. They can be used quite readily. They can also be used to dismantle the facility quite readily. So that's where I see it has inroads. This is typically a slit tape or a split tape fabric, which is spread coated with an olefin plastic, typically a linear low density material. But that's where I see the inroads of it. We're seeing that often.
Okay. Danielle is making another question. Will there be any update on GRI white paper number 6?
Actually, the board of advisors, I just had a meeting. Yes, as a matter of fact, there'll be an update on that next month, Daniel. So,
okay.
Yeah, I'm doing too many webinars. I'm not writing like I used to, so I got to get on it. Okay, crack the whip. You're worse than my wife here.
Dr. Koerner, I think we're done with the questions. We should copy the link of this presentation and send to all the mining sites, all the landfills. We have a lot of irrigation sites now in Brazil in agriculture using a lot of geomembranes, doing a lot of mistakes. And we, as a member of IGS Brazil, I really want to thank you for your time, you're very passionate about everything you say, and this is very nice. And you can see a lot of people you know in Brazil, and I know you've been here a lot of times. And thank you very much. And we expect to see you here more times and talking about other topics.
It's my pleasure. Thank you so much for the opportunity. Remember, we're stewards of the environment. We're just here for a short while, and let's do it right and the best we can. Thank you so much for the opportunity. It's a pleasure being with you. Take care now.
Boa noite a todos. Obrigado a todos pela presença em mais esse webinar. Thanks everyone, and I hope to see all you soon here in this Geotecnia Brasil channel discussing about geosynthetics. Thank you very much.